Welcome to a day in the life of a vSAN IO. My name is Pete Keeler. I'm a Senior Technical Marketing Manager here at VMware in the Storage and Availability Business Unit. I'm joined on stage with Mr. John Nicholson. John, would you like to introduce yourself?
My name is John Nicholson. I'm a Senior Technical Marketing Architect in Sabuaso.
So, just the standard disclaimer, of course. What we have, though, in store for you really is going to skip over a lot of the basics of vSAN. We are going to assume that you know that part already, and we're going to jump into what makes vSAN do what it does. Look at the detailed I/O path as reads and writes traverse through the I/O stack. So John's going to be first covering what that is, looking at various data services as well, how those impact that I/O path, and then after he's done with that, we'll transition over into some of the other things that vSAN does on the back end that also impact some of the I/O and the characteristics that go along with that. So with that said, let's go ahead and get started. John, why don't you take it over?
All right, so one thing I always like to highlight is vSAN is an object storage platform. It is not a clustered file system. This is not VMFS. And architecturally, that decision was made for a couple reasons. One of which, traditional clustered file systems, you have to deal with a lot of locking and additional overheads. There's limits in terms of scalability within a clustered file system, and often clustered file systems end up having to be designed to work very well at large scale or very well at a small medium scale, but trying to have one that can kind of run the gambit and capabilities and have low overhead, they're just fundamentally not as advantageous as an object storage system. So what this looks like under the hood, and this is again always driven by our VM storage policies. So in this example, we have an object being a VMDK here, and we've got a RAID policy, a RAID 1, that's because we've set our failure to tolerate to 1. And so this is going to make sure that the data is distributed in such a way that we can lose one disk or even an entire host here and still maintain operations, still have another copy of the data, as well as have a witness component, in this case for quorum. Note those witnesses, in this case there is one there, but if data was distributed in such a way that you had components across more than 2 hosts, that witness might actually automatically go away. The witnesses are dynamically generated and removed as needed to maintain quorum. The reason for that being is if we did not have a witness, we did not have a third, an odd number of votes in the system, you could potentially do what's called a split brain. And that would mean that if there was a network partition, these hosts could not see each other, you might end up in a situation where a VM was running twice. We have a rule within vSAN engineering that they're not allowed to design something that can split brain. It's just not possible. And so that's why we've always got an odd number of votes on the components on the back end and how they're weighted. Also in this example, we've got a stripe policy. So we've got a stripe policy of 3. We're splitting that object out into 3 subcomponents. Now these subcomponents could be on different disks in the same disk group, or different disks on entirely different hosts. If we had a 4th or 5th host, you might see some of them striped out across the hosts. It's going to opportunistically balance the placement of those based on available capacity and hybrid, the cache hit ratio, and a number of other things like a random seed to prevent a race condition. But all this is automatically handled under the hood for you, that balancing and that placement. One thing to note is those disk groups, those constructs inside the host, those actually are technically a local file system, and we've updated that format several times. One of the challenges with a clustered file system is trying to update and change the data layout significantly while it's running. It's like trying to work on a car while you're driving it. With an object storage system, when we do updates to that data layout, which we've done again several times, you can do it in a rolling fashion, to where if you have a spare host, you can take a copy offline, migrate the data over, reset how that data is laid out in that structure. And so that way you don't end up carrying the technical debt of decisions that may have made sense 5, 6, 7, 8 years ago on data layout as new, faster forms and new different types of I/O devices come out and new data services, things like we've added like Deduplication and Compression come in. Looking at what are all the different kinds of objects associated with a VM, we've first got the VM home policy, the VM home object. The VM home object contains the namespace. It's going to contain things like your VMX file. We also have VM swap. Swap is what happens, or it's basically the location that data is stored if you have overcommitted memory, you've run out of memory, and now you're having to page to disk at the VM level. Note, swap is always reserved thick. It's always reserving its space. It carries an object space reservation of 100%. So if you're not overcommitting memory and you want that space back, there's an advanced setting on the hosts that you can set that swap to be sparse. And my good friend Jason McCarty has got a great script on his GitHub that'll automate configuring that across a cluster. Also, as we showed in the previous example, we had the VMDK as an object. Also, we have snapshots, so deltas and snaps from memory. Now these are going to inherit the exact same policy as the disk they're attached to. So if you have a failure to tolerate a 1 RAID 5 for the primary VMDK, the snapshot's going to inherit that same policy. Another thing to note is the VMDKs each carry their own individual policy. So if we've set a RAID 1 or we've set maybe a RAID 6, a failure to tolerate a 2, or with Erasure code, you could have different disks with different policies. Some of the uses for this is that you're going to get better write performance on a RAID 1 policy versus a RAID 5, the nature of how Erasure coding carries a write amplification. So you could have your log volume be RAID 1, while the database volume be RAID 5 or 6 if it's a read-heavy database and so forth. And I talk about these policies, but here's what they look like. And again, SPBM, our policy-based management engine, really is the secret sauce under vSAN of how it's controlled. Traditionally in a LUN-based world, you'd set your RAIDs or you set your policies, then every VM would inherit that. It was a bottom-up provisioning. Instead, this is a top-down. This is an application-centric. So you can have different policies, again, in the same cluster. And as we look at what these are, we've got our failures to tolerate here, our primary failure to tolerate. We've got our number of stripes, as I mentioned, and these other things. Now, what are the implications of changing this is something that we want to make sure that's exposed. So we have what if APIs. So if you're setting a policy on a VM or you're wanting to change a policy, it's going to, in the right over here, actually show you what the implications of that policy change are. So in this case, because our object space reservation is set to 0, the initial reservation is going to be 0. This is thin. So digging in a little bit on number of failures to tolerate, we've got our primary failure to tolerate in a normal environment is going to be either 0, 1, 2, or 3. 0 is always going to be a RAID 0. 1 can either be, in a hybrid environment, will always be RAID 1, and in all flash, you have the option to add an erasure code for RAID 5, 6. And if it's set to 3, it's always going to be a mirroring option with 4. Now, number of stripes per object. So as I mentioned, this is going to create a RAID 0 type construct. And in some cases, those stripes may be across different capacity devices within the same host or the same disk group. In other cases, it may end up striping out to other capacity devices in completely different hosts. Now, some reasons why you would set stripe policy is if you're in a hybrid environment, ideally most of your reads should be coming from your read cache, the SSD tier, the upper tier within the disk group. But if you're in an environment where you've got a high random read or you've got one VM that's starting to struggle with that, this is going to help with your random read, your cache misses on the back end. The other thing also is by forcing a stripe policy, you're going to use more disk groups. So if you're trying to push disk throughput to a higher level, in an all-flash environment particularly, this would be where you use this policy. Now note, if you've got a very small number of disk groups, you've got a very small number of fault domains, setting this very high, you may not be able to substantiate it. So, and also, if you set the number of stripes to the total number of disk groups in your environment, you may be in a situation where you can fulfill that policy, but if you had a failure, you wouldn't necessarily have a place to rebuild. So, I was going to say this is something that you should use, but only if performance is an issue. It shouldn't be a default setting to go raise this extensively. Fault domains. So I love traditional storage arrays. I used to work with them. I was a storage admin. But one of the challenges you had, if you have this 7 nines, 9 nines of available magic, black box with all these internally redundant components, that box fundamentally sat in something that was, a couple square feet wide. And in order to make it a system truly highly available, you also have to consider things in the environment. External dependencies, things like switches, cooling, maybe just, your good friend Tim, the destroyer of network uptime, accidentally tripping and knocking a power cable loose. We've seen customers want to have availability for their environment, not just be something where they try to make one little tiny area be highly available, and often that area for some reason always gets a sewage pipe right above it, but be able to split their data out to customize the storage system to the unique realities of the environment around it. And so with fault domains, a classic use case for this is to split up the cluster in such a way that you have a rack awareness. You assign different hosts to different racks that maybe have different switches or different power distribution paths. And what this will do is this will make sure that data mirroring, you don't end up with 2 copies within the same fault domain. In this case, this example, a rack. I have seen this used for different floors, or even within a small campus where they had 3 sites. Note, the fault domains, you can't get started with 2 fault domains. It's going to require the number of fault domains you have as a function of what RAID type you're using. So RAID 1 required 3 hosts for 2 copies and a witness. In the case with fault domains, if you're using RAID 1, it would require 3 fault domains. RAID 5, which requires 4 hosts, so 3+1 stripe, would require 4 fault domains, or in this example, 4 racks. Another thing, some challenges to think about with this, there are some secondary impacts though. So if you want to be able to have a fault domain to rebuild into, you may want to have an N+1 on what the base requirement is. So if you're using RAID 1, if you've got that 4th fault domain, if we lost an entire fault domain, we at least have an opportunistic place for placement. Now there are some enhancements to rebuilds that Pete will talk about later that help mitigate this, but it is something to think about. The other thing also is think about resync throughput when you're designing this. As that I/O has to go from, if this rack is lost and that data would mirror over here, make sure you've got high-speed links between your top of rack switching if you're using those, so that data can flow. Stretch clustering was something we came out with 6.0 update 1, vSAN 6.1. It was a good technology, but it had a critical limit. We could mirror data between sites, but we could not protect data locally. And so if you had a failure of an entire site, you would basically be operating in a RAID 0 state. You couldn't tolerate subsequent failures. People, and we listened, customers, they said they wanted additional protection. So we now have the ability to substantiate a local RAID protection as well as the mirroring between the sites. And this allows for some very interesting use cases where you could conceivably lose an entire site in this example and then lose 2 hosts on the other side. A rather large amount of concurrent failures. Looking at what this looks like from a configuration standpoint, we have a primary level of failures to tolerate. And this is a new construct in this case, and that's either going to be 0 or 1, and that's going to set whether that data is mirrored or not. We then have a secondary level of failures to tolerate, and that's the local RAID policy. In this case, we've selected 2, and since we're using a RAID 6 an erasure coding, it's going to inherit a RAID 6 policy. One thing to note is when the writes go across the wire here, so even if let's say we're doing mirroring on the other side, we're not going to send 2 copies of that data across. We're only going to send 1. There's going to be a DOM owner on the other side that will then splinter that data out. So we're not wasting an unnecessary amount of WAN bandwidth. Another thing is from a rebuild perspective, from where the I/O comes in a rebuild environment, is if you have failures on this, I can't click my laser today. If you have failures on this site, it's going to read from the local site. It's not going to rebuild over the WAN unless it can. Unless we've had 3 failures at this site, we're not going to start trying to pull I/O over that wire. We're trying to be WAN efficient. Again, really encourage you to make sure you size those WAN links appropriately though for rebuilds and so forth. And if you look from an I/O perspective, we've got a requirement of 5 milliseconds round trip time. Will vSAN stretch clustering in theory work higher? Sure. But the reason for the support guideline being at 5 milliseconds is because every write has to be acknowledged by the other site. This is a true active synchronous clustering. You can vMotion freely back and forth. And so because of that, if you're waiting on that I/O to acknowledge on the other side, and it starts you're adding more than 5 milliseconds of write latency to every single write that's going through, you're potentially adding some fun performance experiences. Maybe the users will start getting their torches and pitchforks out. The other thing to note is reads from an I/O perspective in a stretched cluster under the hood. They will by default come from the preferred site. And so if you've got your preferred site, you're running your VMs at, we're not going to add that potential up to 5 milliseconds of read latency. We have a data locality at a site construct where we pull reads from the local site. So we make sure that we're not unnecessarily adding read latency. The writes, we have to pay that penalty because we need to make sure that data is atomic and consistent and those writes have been acknowledged. But from a read perspective, by default, we read from the local site. If you have a very low latency stretched cluster, if your latency is below 1 millisecond, though, maybe you want the extra IOPS, the extra performance capabilities of the other site, there is an advanced setting that you can use, the DOM warm cache setting, and that will actually allow you to read from both sites. Again, that should only be used if you have very low latency between the two links. So let's look a little more closely at the actual I/O path. So for a write to come in, it's going to be initiated by your guest VM. Now that write's going to come down through the vSCSI layer, the HBA, and it's going to come to the local vSAN DOM owner. The DOM owner will generally be on the same host as the VM. It's going to look at that I/O, and if checksums are enabled, it's going to generate a checksum. We try to generate a checksum as early in the I/O path as possible. It's a CRC32. That's going to then go out over the wire. Now note, in this case, the VM happens to be on the same host as one of the copies of the data. That happens to be opportunistic in this case. We're not going to have the data follow the VM around like a lost puppy, so to speak. It's not going to unnecessarily generate backend I/O. We don't want to be in a situation where vMotion causes performance inconsistencies. So as those writes go in, it's going to acknowledge to the write buffers of both drives. And in this case, this is a hybrid example. So 30% of this SSD, of each SSD, is reserved for write cache. So if we add a 200 gigabyte SSD here, we'd have 60 gigabytes of write cache per disk group. Now once that write acknowledgement has been generated and completed, it's going to go back and it's going to confirm it to the guest, and the guest will move on with its day. Now on the back end, that data is going to destage asynchronously. So the VM's continuing on, there's no additional latency, and we're going to, in a hybrid environment, we're going to batch those writes together. We're going to try to coalesce I/O that logically, from an LBA perspective, looks close to each other. The reason for this is if we destage that data together, the actual SCSI command set on these backend drives, native command queuing, tag command queuing, they're going to try to turn that, what would have been a random write into what looks more like a sequential write, which is the one thing magnetic drives are good at. They're not very good at random I/O, but if you've got sequential I/O, it speeds that up. So this log structured batching of I/O helps quite a bit. The other 70% of those SSDs is read cache. So looking at a read, when the guest OS issues the command, it's going to look in a couple places for that data. The first is actually a local DRAM cache, known as client cache, that's sitting on a host. There's 1 gigabyte, and there's a data locality construct with that. That data is in the local memory on the local host where the VM is. If the data's there, it's done. If not, it's going to have to go look in the write cache, or the read cache. So in a hybrid environment, that other 70% is reserved for reads, and it's going to go look for that data. And if it can find in the SSD, it'll acknowledge it. If not, you've got a read cache miss, it'll go down to disk. In the event it has to go down to disk, it's going to request, say it was a 4K read, it's going to request that read, and then it's going to try to grab the entire megabyte behind it. And the reason for this is often when you have a read cache miss on one block, you're probably going to have read cache misses for very similar near blocks. And that whole 1 megabyte will actually get ripped up all the way to the client cache in memory and then pre-staged back into the SSD. They've made some significant improvements to your basic adaptive read cache or ARC type construct here. Now, on a read on all flash, again, we have similar construct. One thing to note, the SSD is reserved, in this case, for 100% write cache. So when you do a read, first it'll look in the local memory on the host, see if it's there. Then it will go and see if it can find it on the backend layer. Now note, the data may have been written to that write buffer drive and hasn't destaged yet. So the read actually may come from the write buffer still. Even though it is 100% a write buffer drive, the data may not have destaged to the backend capacity tier yet. And again, going through how the caching works, with client cache, you've got 1 gigabyte that's assigned. It's actually, technically it's 0.4% of host memory up to 1 gigabyte, but in most cases this is 1 gigabyte. And that can read very fast. The reason why that's a data local cache that actually does follow the VM is there's a very tiny amount of data. That being refilled between hosts doesn't cause significant performance problems when you do a vMotion. The latency also of memory is very low. It's measured in very low nanoseconds. SSD seek times, even on a good, a P3700 NVMe device, may be as high as 90 microseconds. The overhead of the network, even with a TC hop of 10, 15 microseconds, is still significantly lower than oftentimes the seek time of a storage device. Now, memory is faster, so that's why, from a memory basis, we try to keep that local. Checksumming. By default, checksumming is on. We do have a policy to disable that if you've got data that's checksummed at a higher level, and so that additional overhead's unnecessary, or you have inferior data sets, you've got test dev environments, you just don't really care about it. You can always disable that. Note, this feature previously had some I/O overhead and amplification. There's been significant gains with vSAN 6.6 and performance of it. We use a CRC32, which can be accelerated incredibly well with our friends in the processor industry. Over 1 million of these can be performed on a single core with relative ease. There's offload functions that have existed for a very, very long time. So this is generated, as early as possible. We're going to generate it on the host that's sending the I/O out, and we're going to try to verify it as late as possible. And the reason for that is not only are we looking for data corruption at rest, we're also looking for in-flight corruption. So once that data goes out to the other host, and before it's destaged, we're going to verify to make sure that data was intact. It's written down. Now, any subsequent read of that block, we're also going to read that checksum. And note, the checksum is not stored. This isn't like a traditional SCSI T10 diff. It's not stored on the same, as part of the same block where the actual I/O is. It's stored separately. This does lead to a mild amount of I/O amplification, but we have a memory cache to accelerate this significantly. And that process means that you're really maintaining data integrity on the read of that checksum. Now note, if a block has not been read in 1 year, if it's a rather old, it's some old cold data, we are going to actively go and scrub. We'll go ahead and read that block, read that checksum, and make sure it's been scrubbed. And this is to prevent slow, silent data corruption in the back end of the environment. Note, that is an adjustable setting. You can set it down to 1 month at the lowest, but the 1 year with modern bit error rates of drives should be more than enough. Deduplication and compression, or space efficiencies, a phrase that I could not say correctly in Vegas. A couple things to note about the dedupe and compression. This is an inline type process, but it is not inline on every I/O. And this is, when we implemented this feature, I got a lot of questions about why it's not a per VM setting. I used to be a storage admin, and on particularly some old hybrid arrays, if you use dedupe and compression, it was an endless amount of checkboxes, scheduling, figuring out which volumes use each on. It was confusing. People generally set it wrong at some point, had performance problems, and then would abandon the feature. We wanted this to be something that the majority of our customers could just check the box, turn on, enable it globally, and move on with life. And actually, looking at some of the phone home data recently, the majority of our customers who are on all flash are using this feature. This is enabled globally across the cluster. So what happens for an I/O is the I/O comes into the write buffer drive like it did before, and it comes in fully hydrated. This is for a reason. We don't want to add the overheads of deduplication compression to data that has a short lifespan. A lot of blocks are written and then quickly overwritten. They've got the lifespan of a gnat or a fly. So why waste the CPU on checksumming and compression then? Now, as the data is destaged to the back end, as it's moved down, we're first going to run a SHA-1 hash to identify if that block is unique. If it pattern matches against an existing block, we were at a pointer and we're done. We're not going to waste data compressing. We're not going to waste CPU compressing data that's duplicate. Next up comes compression. We use an LZ4. And so the compression is going to go through and look at it. We're going to try to compress it. If the block can be compressed to 2 kilobytes or less, we're going to write it compressed. If it compresses poorly, it's 3.5 kilobytes come back. We're going to write it fully hydrated. And this is for a couple reasons. One, we don't want to be in a situation where we're wasting CPU uncompressing data that compressed poorly. Again, we're trying to keep the overheads of this process, of this feature relatively low. In areas where the gain, or the juice that can be gained from the squeeze, so to speak, the gain is very small relative to the compute. We're not going to waste CPU. The other issue is if you can't compress it less than that, you start running into block alignment issues on the back end, you start getting fragmentation. That would require periodic groveling or moving of blocks around. Having to do additional compaction and defragmenting on the back end is wasted CPU, it's wasted I/O, it's wasted memory space. These are all things that just fundamentally aren't worth it. We did choose a 4 kilobyte block grain, which is actually very granular, but these various ways of conserving and harvesting back CPU in this process, not wasting compute on blocks that have a short lifespan and so forth, allowed us to accomplish this with a 4K fixed block. That 4K, that small block, means we're actually going to find duplicate data beyond just basic OS and application binaries that using a larger block would use. Question?
Wondering, in the component placement view within the web client, with a non-deduplicated data store, it will show you exactly which host and which disk a component is on. With deduplication, that component can be spread across a number of disks within the disk.
So actually, my next slide answers this. So the question is where do the components live? In a classic non-deduplicate compressed, you know exactly components on this capacity drive and so forth. Through the nature of deduplication, you can't necessarily choose where the pattern matches are going to have unless you did a significant amount of back-end defragmentation, which would be silly. So what happens is we actually stripe the data internally across those disk groups automatically. The alternative would be every disk is its own dedupe domain, which would be silly. One thing to note, our deduplication domain is an entire disk group, and that's because a disk group to us is a fault domain. In theory, you could get 20-30% better dedupe by doing a global dedupe, but that requires massive memory hash tables. And in the case of a double puncture or any type of issue, you then get global dedupe also exposes you to global corruption. We don't want to be in a situation where a slight issue can cause total loss of data. So data integrity comes first for us over space efficiency. So that's partly goes into this design. Also, striping has some secondary benefits on endurance and maintaining throughput. And again, trying to keep the performance and the CPU overheads of this feature low. Actually, I'll have to look. So, again, going through this process, the VM issues the write. And note, when the data was going from the write buffer to the backend capacity tier, it had to be copied into memory anyways. So we're piggybacking on an existing I/O flow. There's no additional movements of data. Additional movements of data, again, are expensive. And as I said, with the costs, nothing is free, but we're trying to cheat the costs as well as we can. And so by avoiding I/O overhead for metadata lookups, data having to be moved in and out of the write buffer multiple times, these are all things that contribute significantly towards these features having a lower overhead. Compression. One thing to note on that compression, again, as I said, that's LZ4. Our friends at Google have done significant optimizations to the CPU overhead of LZ4. It's an incredibly efficient construct. And if you have got questions about, people always say, well, what's my deduplication, my compression ratio going to be? And they look at me as though I'm some great oracle who can peer into their environment and say, you're going to get 12-to-1 or something crazy. One thing I'll note is if you're trying to get we do have a space efficiencies guide. It's on storagehub.vmware.com. There's a lot of information there. The other thing to note is if you look at your backup reports or you just take some of your data set and compress it, that will give you a guidance about how compressible or dedupable your data is. Oftentimes people have this information by proxy from other systems that are compressing or deduping data. Now, if you have compressed JPEGs, obviously they're not going to compress well, but if you've got things like databases with large blocks, that tends to compress quite well. Another thing is if you've got legacy operating systems that are not necessarily thin friendly, there are cases where it's using tools like DD or SDelete with the flag to send zeros. That can send zeros to the backend and allow basically the deduplication compression engine to harvest that capacity back from a space reclamation. I'm going to try to move quickly here to catch up for Pete section. So erasure coding, RAID 5 and 6. RAID 5 is a 3+1 stripe. That's currently fixed today. We didn't want to add too many nerd knobs. In theory, the erasure coding on the back end could be changed. If you've got a good business case, you're welcome to go argue with Christos about that. RAID 6 is a 4+2. And so that comes again from the failure to tolerated 2. There are additional write overhead on this. And this is implemented on all flash. And a lot of people ask why we did this for all flash and not try to implement this on hybrid. Again, you've got the write overheads, from the front end perspective, and the all flash can handle that and sustain performance. And even in a hybrid, there are ways you could try to cheat that, but one of the challenges comes in not from just the write overhead with erasure codes, but one thing to remember about erasure codes is a rebuild. If you've got a damaged component, you're now having to potentially read the entire full stripe while you're doing a rebuild. You potentially have anywhere from an 8 to 16x amplification on the back end of I/O going on from a read perspective. So there's a lot of, this is something that really all flash can deliver in a consistent performance, and we wanted to deliver this feature in such a way without compromise that you aren't having to overly worry about those overheads causing issues in the environment, especially during a rebuild. I was going to say, I use the word erasure code, and occasionally someone will say, well, that's not erasure coding, that's RAID 5. Well, no, it's the actual Zor logic and Reed Solomon, these are erasure codes. And Christos has a very good blog on virtual blocks discussing the actual Planck theorems and the math we used to keep this CPU efficient. I always like to say this is space savings. There you go. Almost said it right first time. That you can bank on. So some people, as a policy, they don't want to use deduplication compression because they want a predictable amount of capacity. No one's going to be monitoring the environment from an overcommitment standpoint. This is something you've got a bit more control and visibility. If it's an environment with not necessarily going to be monitored as extensively for capacity usage. Now, vSAN encryption was something that came out in vSAN 6.6, and a quick thing to note in terms of the I/O flow is the data is encrypted at rest at all times. The data is going to be written to the write buffer, encrypted. It's going to be encrypted before it goes in. It's decrypted when it comes out to memory to destage, and while it's in memory, we apply our deduplication and compression, and then it's re-encrypted before it goes back down. So at no point is the data at rest unencrypted, but we can still do deduplication and compression, which historically would effectively not work if the data was encrypted at a higher level, ingest, or possibly using VMencrypt that was enabled in 6.5. Now note, data in flight is not encrypted with vSAN encrypt. This is data at rest encryption. The analogy Mike Foley likes to use comparing VMencrypt versus vSAN encrypt is vSAN encrypt, it will hit your compliance type requirements for data at rest. It protects you from someone going in and walking out with a arm full of hard drives. VMencrypt allows immutability of the actual admins if you're using no crypto, and that protects you from the guy walking out with a thumb drive, so to speak. As I mentioned with swap, you can set that thin, look in your space and your capacity monitoring, and if you're seeing you're using a lot of swap, here's the advanced setting you would use, as well as Jace has got a great script to change that. From a snapshot perspective, vSAN does not use traditional VMFS snapshots or sparse SE snapshots. vSAN uses its own snapshotting process that uses a memory lookup table for common blocks. There's a 4 megabyte extent. There's actually a great presentation that was done at VMworld 2 years ago called Snapshots Suck that goes into greater depth on this. By the way, has anyone ever seen a snapshot chain this big? Is anyone a little terrified at seeing this? I am. So from a performance perspective, you can run vSAN snaps for a very long time without necessarily the traditional overheads where performance would deteriorate rapidly to 80 or 90%. Typical performance overhead of existing, in a steady state environment are going to be 5 to 10%. For merging of snapshots, we leverage a mirror driver that was introduced. It actually comes from storage vMotion back in the day, rather than helper snapshots as of 6.0. And so when snap merges, where you would potentially have a helper snap, and if you had a lot of writes coming in, you'd have these helper snaps that would potentially keep creating and backing up. We're not going to have that problem with vSAN snapshots.
All right, John. Well, thank you very much. That was a really good understanding of the data path as the VM sees it, and all of the activities with regards to the data services that are provided by vSAN. But there's a lot of other activities that are going on in the back end of vSAN. And in fact, actually, this is something that happens really with any storage system. If you think about storage systems and what they're responsible for, you're looking at things like availability, redundancy, and the data services. So it has to do those things. It has to provide those services in some way. But most of the time, in a traditional infrastructure, you wouldn't be able to really see those things. So think about oftentimes you might look at a storage array, and the only indication that you might see that it was really working a lot was the fan speeds, simply increasing. You might have metrics of that array, but you wouldn't really be able to tell what's going on. Well, with vSAN, we expose a lot of that information. So we basically divide up the type of I/O that we have really in two basic terms. Here we have the front-end VM traffic. This is the reads that are being requested by the individual VMs and the writes that are being fully committed by the individual VMs. So one read I/O is actually one read I/O. But there's other traffic, that being back-end traffic, that is the result of other activities that are going on in vSAN. And that would be things like replica traffic. If we want to write data or have data in multiple locations for that purposes of redundancy, we have to be able to write it to multiple locations. So that's where that replica traffic would come in. If you are doing a mirror in just a classic sense, that one write on the front end VM would be a single I/O, but then on the back end it would be 2 I/Os. And if you had a failure to tolerate of 3, then it would be 3 I/Os. And so you have that the write amplification that would typically occur whether it be vSAN or any other storage system, in fact. Now, there are other types of back-end storage traffic, and this really relates to the idea of the fact that vSAN is a distributed storage system, so it has to place data in multiple locations where the storage devices actually live across the host. So you have things like the resynchronizations of those objects or the components that make up those objects, just like John showed earlier in the presentation. And those resynchronizations would really occur for a variety of different circumstances. One might be an object policy change. So if we said we want a VM that has a failure to tolerate of 1, and we want to make that a failure to tolerate of 2, that means that it's going to have to make an additional copy of that. And how is it going to do that? It's going to do that automatically for you in the back end, but and it's going to report that through the storage policy-based framework and the management of that. You might also see that back-end traffic occur if you're doing a full host evacuation. Let's say you're going to decommission a host. It has another purpose. That data has to move off of there. And in order to meet the initial performance and the protection policies that you have associated with those respective VMs. vSAN will also be very intelligent when it comes to the placement of these objects and the components that make up the objects. So it's going to rebalance the data as it sees fit. And we're going to jump in to that a little bit, or in a little more detail here shortly. And then finally, we have object and component repairs. This is when vSAN recognizes that something is out of compliance. It's whether the objects are essentially absent, or if it actually received a SCSI sense code and says, you know what, we need to rebuild or repair some of that data in order to bring the objects back up to full compliance. One of the things, though, to keep in mind is that because vSAN is built right in to the kernel, we have really unique insight in this, is that not only do we have full control of the IOs as they traverse throughout the stack, meaning that we own the scheduler that manages those IOs to and from. We can change and adjust the priorities based off of the conditions that it sees as it is occurring in the cluster. And we can also provide really good visibility of that data, and thus being in the performance graphs as we see here in the lower part of the screen. And we get very granular in the various metrics that are going to show this data. So repairs and rebuilds. So the basic fundamentals here is that in this particular case, we would have a 700 gig VMDK. This would be seen as a single object. And then we have a policy that is associated with that of RAID 1, essentially a mirror, and a failure to tolerate of one. So we would have two objects that make up that as a valid policy, and then one witness component. Now, in the event that one of those objects or some of the components that make up that object is not visible for some reason, or not available for some reason, vSAN's going to make note of that. And again, we know that across any sort of a network, there's going to be transient errors of some sort. Things may go absent. There might be a little blip in your network, and we don't. Yeah, there you go. Somebody, yeah, they hit the wrong button. Is usually what happens there. But in the case here where we don't want to be overly aggressive in saying something went absent, wow, we need to rebuild right away, because we don't know if it is a transient state or not. Now, if we do receive an actual SCSI sense code via the disk itself saying that it's
physical device loss.
An actual physical device loss where it is no longer functioning, then we will initiate that rebuild process right away. How many of you are running vSAN 6.6? Can you show of hands here? All right, very good. So what I'm going to show here actually in the next few slides is really a result of a lot of improvements that we made with respect to vSAN. And the majority of them were introduced in vSAN 6.6. That's why if you've heard in other vSAN sessions here at VMworld, if that ringing endorsement of saying upgrade to the latest version, this is why. We've really taken a lot of emphasis in being able to improve the efficiencies of resyncs and rebuilds and repairs throughout vSAN, because the fastest rebuilds are the ones that never happen in the first place. So we're really mindful of reducing the amount of activity that's occurring on the back end if it's not necessary, and that thus will improve the performance of the front end, or the performance that the VMs will see on the front end. So one of the enhancements here is this notion of enhanced rebalancing, in the sense that in situations where you would have a vSAN cluster in which you had devices that were nearing around 80% in capacity, vSAN would automatically look to rebalance the components so that they would satisfy that and meet that lower threshold. But one problem would come up in these vSAN clusters that were much more full is that they may not have a location for the component to move to. So in vSAN 6.6, we introduced this notion of enhanced rebalancing, meaning that it could split an individual component into smaller chunks. And what this does is that then it can redistribute these components in a much more even fashion. And when you do that, you have actually increased the effective capacity of your vSAN cluster because you have more opportunity to place that data elsewhere. And this also helps with further maintenance activities like entering a host into maintenance mode and things of that sort. We've also improved some of the logic around the placement choices of those components as it's rebalancing. One thing that can happen in any sort of a distributed storage system, and even in vSAN, is that you can have a chain reaction effect of the components, in that if a certain component is placed on host B, then it realizes, oh, now it has to move another component elsewhere. We really want to reduce that chain reaction that occurs there. vSAN is going to be smart enough to understand where it can place the components that still satisfy the policies that have been assigned to that actual object. We've also introduced in vSAN 6.6 the ability to throttle the resyncs. Now this had come up in a number of cases where there was an abnormal amount of resync activity, and we really needed a way to provide some control of that. And now VMware still recommends that this is only to be used in corner cases and not set just explicitly in left. It is one thing to note: anytime that you do throttle the resync traffic, that's only going to slow down the resyncs. It's not going to speed up the resyncs. This is simply a matter of giving more priority to the VMIO traffic rather than the resync traffic. And all of this, by the way, is now visible in the performance service of vSAN. And that was one of the things that I was really excited to see, because now you can see how much activity is as a result of resyncs right within the performance service of vSAN. An additional improvement with regards to these rebuilds was through this smart, efficient repair. In versions of vSAN earlier than 6.6, what would happen is that when a host would go absent, in this case, it would wait for that period of time before it would kick off that rebuild in order to satisfy the protection policy. But once it would start, it would run until full completion of that rebuild. Well, what would happen is that maybe you might have a host that went down for a period of time, but it would come back up during the time in which the rebuild was still occurring. Well, that presented a problem, because now you had this rebuild that no longer needed to continue, yet the host came back. So with vSAN 6.6, we have the ability to make the determination: if a host comes back during the time in which a rebuild is active, it's going to analyze what the current state is, and it's going to make the call on which method should it use. Should it simply resync or update the host that just came back online, or is it going to continue with the rebuild on that new pristine host where there was never any data on there? This is really this improved logic again has really come up. We've had cases where you might simply have a host that had a lot of maintenance activity, a lot of updates, whether they be firmware updates, things of that nature, and it took just a little bit longer than 1 hour. And here now that's going to help reduce the number of resync activity that's actually going on.
Is tunable. You could adjust the APD timer, but
Yeah, it is fully adjustable. That's a great point, John. We do recommend that you leave it as is. There's always a fine balance there, really, on anything, and we've been, I think we've received from several data points, anyways, that 1 hour seems to work out fairly well in most cases. So an additional feature of 6.6 that really changed and really helped improve this idea of resyncs and rebuilds was this notion of a partial repair. And think of this as a more opportunistic way of repairing data that is no longer available. So here we have a situation where we have a 6-node vSAN cluster. We have a policy of FTT of 2, meaning that there's 3 copies of data. It can suffer 2 failures. And of course, there's 2 witness components just for the sake of, as John mentioned, we never want to have a situation where you want to split brain something. So that's really just to keep the vote count as needed. So let's imagine here we have a double failure of some sort. Maybe they went down at the same time. Maybe one went down shortly after the other one did. So we have the configured policy of FTT of 2. We have an effective compliance of FTT of 0, meaning there's 1 copy of data left, or 1 copy of data available. The VM's still up and it's still available, but you can't suffer another loss at this point. Now, what we're going to do with this notion of a partial repair is we are going to rebuild or repair in an opportunistic fashion where we can, if it increases the actual effective compliance. So we were at an FTT of 0, and it saw that it could move up to an FTT level of 1, and so it did. And it's still going to wait. If there's a situation where another host becomes available, then it's going to complete that repair process. Now, you might look at that and you think, well, wait a minute, we have 3 replicas. How come that isn't an FTT of 2? Well, it's because you only have 1 witness component. And if you note here from the slide before, here, I'll back up here, you'll notice that the replica object actually replaced that 1 witness component. That's because we give full priority on the data itself, on the copies of data before we do the actual witness component. The witness component is really small and it can be created almost immediately. And so by giving this full priority, then when another host comes back online, just as we see here, now we have full compliance and you're back up to full FTT2 at that point. And by the way, this was really a significant improvement in the situations with stretch clusters. This is topology aware, meaning that just as the example that John showed, you can have a case where there was a double failure and it can opportunistically repair where it can, whether it be on a single site or across sites. So I think right now, actually, let's jump into maybe a little Q&A since we have a few moments left. Sound good, John?
Yeah.
All right.
Question? Yeah.
With that last example, you said that's new behavior in 6.6.
Yes.
So in 6.5, it would have left the witness in place and just put a new component on the
It would.
host, or it would have done nothing?
So it would have done nothing.
If it can't make, yeah.
Yeah.
With basically what happens is prior to that, it's if it can't meet policy compliance, unless you're using, there is an odd case of forced provisioning, but that's a whole nother bag of worms. It would not make an effort to make an additional copy. These slides, they'll be available after the conference.
Right there. Right in front there, yeah.
Do you have thought about hash collisions with Dedup?
SHA-1 with a 4K fixed block, your hash collision chance is 1 in a couple exabytes. It's comically large. It's not a variable block. Variable block would actually expose you to that. The other thing also is the dedupe domain, again, is only a disk group. So even if you're using fairly large drives and the maximum theoretical hit is 16 per capacity device, 16 times 7, you're at about 100 terabytes for a potential collision domain. Just from the math there, as well as you also, that's not really a practical concern. Okay. I was going to say there's other systems, most other systems out there actually cut it a lot larger, either by doing global dedupe or doing a variable block, but that fixed block significantly reduces that too.
Hi, is there a reason why with encryption you decided not to have encryption done at a high level, so before the traffic gets sent across the network? Why is it? Because you're duplicating the effort by encrypting on 2 hosts with RAID 1 or more with FTT higher.
So the question is, why do we not encrypt at a higher level, encrypt it on the DOM proxy versus that? So if you do want to encrypt all the way at the vSCSI level, you can do that today with VM Encrypt. And that will give you in-flight encryption. That said, that is something that breaks deduplication and compression. You could try to shift it to the DOM proxy owner, but that's a different place in a logic in terms of where the I/O services are implemented. That's something I'll ask engineering about. The key things, though, is one thing to note is traditional storage protocols, none of them are encrypted over the wire. I mean, NFS, FC, iSCSI, in theory, FC layer 3, you could insert that service, but it's never been done.
And is there a reason why snapshots behave similarly to why they're redo logs rather than the VMworld way of doing things?
Well, VMworld is offloading to the array, so we're not an array on the back end, so there's nothing to offload to.
So why is the snapshot not being performed down at the vSAN level? Why is it still being performed higher up in the stack, like VMFS?
It's not really higher up the stack. I mean, fundamentally, this whole layer is native to us. And again, we're not a clustered file system, so doing a file system snapshot in a distributed fashion would be kind of bizarre in that regard. In fact, that would be adding additional overheads. There was a session on a tech preview of some further enhancements to snapshots. I'd encourage you to look at that or ask for an NDA briefing about some other things potentially.
Yeah, there are some similarities, of course, between vSAN and vVols as how it's presented, but of course on the back end and the activities that's going on, a lot of those responsibilities are actually taken care of by a storage array. So,
and there are some similarities, but the key things to remember is we do have a memory-based pointer that we're tracking blocks, so you're not paying the full choose your own adventure book of hunting down blocks like you would have with a traditional. As well as, again, on merges, we're not using helper snapshots anymore. We've got that mirror driver. And those two remove a lot of the key stun pain points that are traditionally associated with a snapshot.
All right, anyone else?
Anyone else? All right.
All right, thank you, everyone.
Remember to fill your surveys.
Yes.